So thanks, Edwin. So today we have Edwin, who most of you will know. So I'm guessing everyone has been to the BVI seminars before. Basically, we try to organize these seminars focused on vision in the broadest sense, and it brings sort of interdisciplinary audiences. And this time we have Edwin, who is a really great speaker. So Edwin did his PhD in experimental psychology in Oxford, and then he went to do his postdoc in the other place.
Not too much.
And a lot of Edwin's work sort of focuses on, I guess, quantitative approaches to cognitive questions, from trying to understand development to sort of arms race between pigeons and humans, to taking guts in people's stomachs. So he's basically kind of like a wild card, and that's some really interesting stuff. And Edwin is also one of the nicest people I know. Like, he does a lot of contributions to open source software, anything in eye tracking. If you don't see Edwin's name, you're probably in the wrong place. So just a great person to have around. So today, I'm going to be talking to us about eye tracking without the eyes, which is really nice. So no disgusting images or arms raised pigeons this time. Or maybe
Can't make that promise fully, but I'll try to keep that lower.
All right, over to you, Edwin.
Lovely. So yeah, it's a shame that Elio mentioned all of my actually interesting work, because this is quite possibly the boringest thing that we ever did. But it's a very useful thing. So I'd like to talk you through it today. And just to kind of fend off the inevitable boredom, I'm just going to give you like the basic bit of the talk in a couple of seconds. You can leave after this summary and you will have missed nothing. So essentially, the problem is that we do a lot of eye tracking. And this thing happened that made it quite impossible to be in the lab for a while. I'm sure you'll remember, it was around 2020. And suddenly there was this need for doing online research. And to be fully honest, this project kind of precedes that. And it was by coincidence that it became like very much the forefront of, I guess, people's attention. But the basic idea is that if you do eye tracking, you need something in the lab that does the tracking for you, right? Specialized camera, infrared light, there's a whole bunch of software going on to kind of extract the data that you need from these really kind of nice specialized setups. It's hard to replicate at people's homes. And we'll talk about webcam eye tracking in a bit. But we tried to find a solution, and we found a solution. So basically here on the top, we have gaze movements on two images. On the bottom, we have our mouse movements, which is the approximation that I'll explain in a second. And I think the kind of overview of this is that it's the same. So that's a short summary of the rest of the half hour or whatever. If you want to leave, again, you're not going to miss too much more, because what I'm going to kind of explain is that these two things are more or less equivalent. So yeah, and just to kind of ensure that you realize I'm not a zealot, there are options for eye tracking on the web. This is me trying to do this in like 2013. So I've been like doing webcam-based eye tracking for a little while now. And it's a really cool technique. It allows you to basically just use a consumer webcam, extract an eye image from like a larger image, and then try to do things like finding the pupil, finding out where someone is looking, using a bit of a calibration between like pupil corneal differences and where people are looking at a screen, much the same as normal eye tracking. The downside of this is that it doesn't really work particularly well. And that's true in the sense that many people won't even start doing this because they don't have an eye tracker. So you're excluding a significant part of the online population. And the whole promise of doing testing in a kind of web environment is that you can test everyone in the whole world with an internet connection, right? So by then reducing your sample straight away, you're kind of defeating the purpose a little bit. The other aspect here is that even if people do have a webcam, attrition is exceedingly high. About 50 to 60% of participants you'll lose because of them not finishing the calibration, them not really wanting to, or them literally not being able to, depending on the circumstances that their webcam is in. You need somewhat decent lighting, no reflection on the screen, on the cornea. There's a bunch of like very boring stuff that needs to be met in order for this to actually work. And then even if you get it to work, if you get people to the calibration, sometimes the accuracy is just too low to actually get them to be properly tested. So you're losing again up to 50 or 60% of your participants if you're trying to do your kind of eye tracking methodology from the lab online with these webcam-based tools. So they do exist. They're just not particularly good. And even people who use this very heavily would argue, well, you don't really use it in the same way. Maybe you do left, right on the screen, quadrants at best, but the specificity of these webcams isn't high enough to go deeper than that. So smaller areas of interest, you can forget about. So again, not necessarily a zealot, but also it's not the perfect tool like, lab-based eye tracking is, which we can all agree, I think, is the perfect tool, right? So we try to find something that worked differently. And the solution we came up with is essentially the stupidest thing you can possibly imagine. We have a cursor that's human guided, right? That's just a cursor that you use on the internet. We take whatever stimulus display we have, we give that a good Gaussian blur to represent kind of peripheral vision, which is, very low resolution. And then around the mouse, we draw this aperture that isn't blurred. That's a nice and crisp, clear image to represent the fovea. There's a bit of a gradation between the two, so you don't have hard edges that could draw attention. But this is it, right? Now you have this aperture that can follow the cursor around, so people can guide this kind of spotlights or cursor-locked aperture across a visual scene. And suddenly you have like an eye movement analog. So this is, as I said, quite like this is the first thing that you would think about. And I guess I don't usually think deeper than that. So that's what we went with. It's also not us who invented this, right? This is something that's been around for a little while. So you can go all the way back to the 70s, where Ian just explained this earlier. Machines weren't necessarily quite the same as they are now. But Keith Rayner took this into the lab and basically looked at people making eye movements in reading situations, but he locked out part of the, or at least he only unlocked part of the screen and the rest was all blacked out. So there's a nice kind of example of this thing in eye trackers, and since it's been used in a ton of different ways to kind of approximate eye tracking. There's slightly different text. Some people follow like a cursor around, other people explicitly make you click on a display to kind of unlock what's under there. There's a bunch of different approaches, but they all come down to roughly the same idea as what I'm going to show you today. I think this is kind of the most sensible approach to doing things, but I'll also show a few of those spotlights where instead of a blur, you have just a complete blacking out of the environment. Right. I say we, because this is developed by Alexander Irvine, my PhD at the time, who has since moved to greener pastures, works for the AI Safety Institute now, does much more cool stuff than this, and Tom Armstrong, who is a pathological user of very cheap eye trackers. It's literally his favorite thing in the world to do. He has an eye link, just gathering dust. He just uses these very cheap things. And he thought, what else can I do to further degrade my data quality? And this is therefore the next project. Papers published in Behaviour Research Methods, if you want to read it. You don't have to at the end of this, because again, it's a very boring talk. I'm just going to guide you through basically all of the materials that we have in there. It's also free software. So we've just given this out as open source. You can use the JavaScript library yourself, but it's probably easier is to use its already implemented version in Gorilla or other platforms you might like Pavlovia using PsychoPy, or we have a JSPsych compatible stuff as well. So whatever flavor of experiment builder you like for lab-based experiments, this should work with it. And there's also people who use this in very custom kind of environments. So some of those examples will come up. Right. So the main point here is now we have this thing that on the surface, at least, seems somewhat similar to the human visual system and to eye movements. Now we need to test whether that's actually true, right? Is it deeper than surface level actually similar enough as well? So we're going to do first is just kind of looking at the validity. How much does this actually overlap with eye movements? Then thereafter, we're going to look at reliability. how consistent is what I'm getting from my data. And then thereafter, I'm going to go through a few more examples, because here I'm going to use something that's really heavily inspired by my own work, which is this preferential looking paradigm that I started with. It's a very stupid system. You put two stimuli on the screen, usually photos of some kind of semantic meaning. In my case, a lot of it is disgust related. I don't think I have many of those photos on here without a blur, so you won't be faced, I think, with poo, but maybe you will. I actually know. And the other side is usually a neutral one. So it's interesting to see kind of, gaze behavior towards either of these stimuli. Do they avoid nasty things? Do they look at like more pleasant things? And this is essentially a design where we used a pre-existing gaze study and then collected an online sample as well. And essentially what you see is that the movements are roughly somewhat similar. Right? This is a nice anecdotal example. Each of these stimuli, each of these circles is a single individual, and the heat map afterwards is their aggregated data. That's for a discussed neutral pairing. This is for a nice pleasant pairing. And I think with this one, keep an eye on the heat map afterwards, because you see a lot of kind of overlap in gaze behavior between them. So all of the faces were nice and hot. There's this affordance kind of movement or looking kind of behavior towards something on the, what you even call that, the tool on the right. There's some focus on where it hinges. So there are these nice kind of overlaps. So from a kind of anecdotal point of view, this seems to be at least capturing some of the gaze behavior that you would see with eye tracking. And this is the overview of that kind of quantified few different discussed pairings, few different pleasant pairings. Top row here is gaze, mouse, gaze, mouse. The mouse screen is always a bit smaller. We use the Gorilla implementation, so you basically, the browser bar you lose. And this is the full screen. But yeah, the bottom line is that if you kind of, from the distance there, squint a bit hard, but the overlap between these pairings is really like rather striking. There's an overall kind of similar heat map between all of these. So at least from this kind of anecdotal way of looking at data, we would say, oh, roughly there's an overlap, right? So mouse movements approximate the gaze movements reasonably well. One could stop there, but obviously this is not necessarily data that we're trying to get at. There could be different temporal patterns underlying this as well. So this is just a like promising first start, but what we usually get from this is a different score between the neutral and the, in this case, disgusting stimulus. And this is a nice kind of, I appreciate not everyone here does this kind of research, but bear with me. This is a nice kind of model system to test this in. You see this really striking gaze behavior where typically when presented with this kind of situation, people first, and you see that in the first kind of second on this graph with this kind of upwards movement, that's a bias towards whatever disgusting photo I'm showing them. That's some kind of initial morbid curiosity, if you want to call it that. And it's just a bias towards this thing that then immediately turns into a bias away from the thing. Everything under the dotted line is kind of a gaze bias away. So it's a pretty well described phenomenon because we keep beating this drum in the literature. So this is a nice kind of, I guess, system to try and approximate. There's the gaze behavior, and this is a nice heat map showing the same thing. Purple is approach, green is avoidance. There's another condition in here where there's pleasant images and people tend to look at those for sustained amounts of time. The different lines are repeats of the same stimuli. And one of the interesting aspects here is that it's also quite stable across different presentations. So that's the gaze. And this is the mouse kind of equivalent of that. And we see a few different things replicated. So first of all, we have the sustained bias towards the pleasant images and away from the disgusting images nicely replicated, right? We also see that there's, at least on the first presentation, during those disgusting stimuli, a bit of a bias towards the nasty stimuli as well, which seems to reflect that morbid curiosity. So that's a nice replication as well. What we also see, though, is that the movement away from the center and towards either direction is a bit slower, and the movement away from the discussing stimulus is also a bit slower, which could likely reflect the fact that people are moving a cursor around, right? So it's not necessarily as fast as these ballistic eye movements that we make at I don't know how many degrees a second. You could look at this in a more formalized way. I just described them verbally. This is the actual difference graphs between the two populations. So the mouse study and the gaze study. And again, the gaze study was pre-pandemic. The mouse study is during, I guess, pandemic lockdowns. So these are different populations. So we're kind of comparing not entirely the same thing. I have a within participant study later. So the idea here is essentially that we have those two populations plotted out. And indeed, what I was just saying, right? You see somewhat similar scores around the avoidance, but you also see that kind of blip at the start that's slightly different, maybe reflecting the speediness of eye movements. And if you do the, for all my Bayes nerds out here, what we're essentially describing is a null effect, right? Because we don't want to see a difference. The graphs below represent the Bayes factors, or the log Bayes factors of the difference between these, with green values indicating a very strong bit of evidence for a difference, and brown colorings. Don't know why we went brown there. Discuss researchers. Anyway, on the scale from vomit to poo, when you're in the kind of brown zone, that's strong evidence for the null hypothesis. So essentially what we're seeing primarily here, but also mostly there, is that there's reasonably strong evidence for not a difference between these two methods of data collection, aside from that very early bias that we can't really replicate with the mouse. As I said, this was two completely different samples, one gathered online, one gathered in the lab. This is a slightly better comparison where we did a within participant replication. So once it became okay again to do research in the lab, we got a bunch of people in, made them do an eye tracking study and the same study in mouse view. And now we have a much stronger kind of lack of a difference effect. But also, especially within the kind of discussed condition, you still see that kind of early bias that might or might not reflect a speed difference, or maybe a overt versus covert type of, well, automated versus reflexive attention. Reflexive versus, doesn't really matter. There we go. So the other thing we want to know, this obviously is neat, but when you take these things into the wild, a more sensible way to go is kind of correlating. So seeing whether there's individual differences in gaze behavior, whether they map onto individual differences in mouse behavior. So we're seeing here on the x-axis the gaze dwell time on a stimulus. On the y-axis, the same thing, but then for the mouse. And what you would expect is that for the same stimuli, if I show low attention towards one, or at least if I try to avoid one stimulus or look a lot at one stimulus in the gaze experiment, you would expect the same in the mouse experiment, right? So that's this correlation, and it's a reasonably high correlation. So people tend to show the same behavior, whether they're doing mouse viewing or gaze viewing. The interesting bit here is that so this is the correlation across the entire trial, but again, this is a dynamic process, right? And if you look at the correlation over time in the trial, what you see is that indeed that early bit, the correlation is kind of within the zone of can't really tell, and only thereafter do you see a positive correlation between the two. So this again kind of reflecting that early, maybe reflexive attention that we can't really cover. Yes.
This is dwell time on what? You kind of divide the images into.
So this is the dwell time in a disgusting stimulus.
Oh yeah, it's on the
yeah.
image. Yeah.
So it's also expressed as a proportion, or is the percentage point difference between a disgusting and a neutral one. So what we're seeing here is that most people are negative values, so they're mostly looking at the neutral stimulus, and therefore you get a negative value over there. For the other set of stimuli, the pleasant stimuli, you see the opposite, that they're kind of looking more towards there. But yeah, it's a difference in percentage point. Sorry, it's a percentage point difference between the two stimuli. So same thing for the pleasant stimuli, slightly lower correlation, but still a reasonably high correlation between the two modes of data collection, and that seems to be somewhat sustained throughout the trial, but you miss the early bit. And again, that might reflect just a slowness to get to where you want to be with the mouse, or it might reflect some kind of reflexive thing with eye movements that you can suppress with these overt movements that you make with the mouse. So from that, we concluded that mouse view is mostly valid in the sense that we see very similar patterns between. You might miss this early, maybe an involuntary component, maybe a component of just actual kind of, physical speediness. But also the kind of gaze biases in these preferential looking paradigms are really nicely replicated on mouse view. Cool. So next question, if we test someone, do we get the same value if we were to test them again? Like, is what we are measuring very stable here? And as experimental psychologists, we often kind of miss that step of our process. We devise a new task, we test a bunch of people, and we assume that what we measure is actually something real because, we do experiments in the lab. Of course it's real, right? We're not like this questionnaire researchers. Who, to their credit, do often do these kind of reliability checks, right? They look at internal consistency, do different items on my questionnaire, measure the same thing. And if anything, this is, I think, something we should maybe move a little bit more to in our field as well. Like, do our different trials test the same thing? So to that end, it's slightly different in this kind of scenario. Because we don't have different items on the questionnaire, but it's also somewhat similar, right? In this case, we have the same photo shown to people, and we also have photos of different kind of content, semantically related photos, I guess, shown to to people. So you can actually compare between those, right? And this is one example of that. So on the x-axis, we have 5 different stimuli. On the y-axis, we have the same different stimuli, and we basically look at the correlation of dwell times across all participants between those stimuli. What you see for disgusting stimuli is that people respond somewhat similar to them. So the way to read this is that the more green this is, the more likely it is that I, on image 1, show the same kind of avoidance pattern that I do on image 2, 3, 4, and 5, and so forth. So this is when I test that with eye tracking, and it looks like pretty stable between different stimuli. And this is when I do it with mouse tracking, and then on the right is the kind of formalized difference between these two correlations. And what's important to realize is that these are all low values, close to 0, and this is where my statistically significant differences would appear if I had them. They aren't appearing there, which again means like null effect. I don't really know why we didn't do that with a base factor. I'm now realizing that would make much more sense. Anyway, here's the Fisher Z transform, and there's no difference. That's the main point. The more pleasant stimuli were a little bit different. There's a slightly lower correlation between those, which is just kind of showing that the internal consistency of that test is slightly different. I don't really know why. These are standard like IAPS images. There were a few more faces in there, so maybe this just reflects a slightly different way that people look at other people, although there's also faces in the disgusting things. I don't really know what this means, but I do know that the low kind of coherence is mapped on between mouse view and gaze movement behavior. So you're kind of capturing the same difference in, or at least same low overlap between stimuli. And again, lack of differences there as well. So this is a nice kind of, I think, illustration that the behavior is quite similar between mouse and gaze again, even if the behavior itself is of different types of reliabilities between stimuli. Another way of looking at reliability is consistency across measurements. So this was something you might expect is different, right? We use different stimuli, so behavior to those stimuli might be different. What we could do is look at reliability in the sense of coherence within the same trials. So we have 4 times, I know how many, 5 stimuli, so we have 20 presentations in our design, which means that we can look at Cronbach's alpha, internal consistency of a questionnaire. You can compute the same thing of internal consistency of trials, right? What you could also do is create these random split halves of your data and then see whether one half correlates with the other half. Do that a bunch of different times, and you come up with something called Spearman-Brown's row. And the higher that is, the closer the correlation between the two halves of your experiment, right? So this is, again, another measure of reliability, but more within an individual. So on the left are eye tracking, on the right are mouse view in red, and there's the row values, so the split half. In orange, there's the alpha values, the chromas alphas. And we see is that eye tracking, at least for the discussed stimuli, has a very acceptable split half reliability and a very respectable 0.8 about for both internal consistency. And we replicate that with mouse view as well. In fact, these are slightly better. The pleasant stimuli were like slightly lower reliability. We already saw that in the kind of behavioral comparison. But it's important to note that they're kind of similar between the gaze and the mouse. Also similar in the sense that when we replicate, sorry, one extra thing, that's the discussed pleasant thing. When we did this again in the lab, I don't really know why this is, but the internal consistency and split half reliabilities went up a little bit. Again, don't know why. Maybe post-COVID, people were looking at these photos in a fundamentally different way. It was a weird time. Our participants were also a different type of sample, although not necessarily. These are plucked out of prolific, so literally a pretty decent, not quite a representative sample, but more representative than the kind of sample that would go in the eye tracking bits where it's just a bunch of students, right? Anyway, the bottom line is that on the types of measurements of reliability, we see that this is actually a really reliable task, but also the mouse equivalent is an equally reliable task. So if you want to use this tool as kind of a stand-in for eye tracking, at least for this task, that's an entirely appropriate thing to do. Right. So I promised a really boring talk. I think I've met that brief. At this point, you're probably thinking, this dude is trying to compare a completely like stupid idea, very simple. It is literally just an aperture locked to the mouse. Why did you not stop after the first 5 minutes, right? And then also I just use preferential looking, which I'm very interested in, and most baby researchers across the road are also very interested in. But by the time that like people grow at about 5 years of age, you can make them do more complex cognitive tasks. So why would you still rely on this? So many of you might be wondering, but I have this other eye tracking task I want to use. Do I port that to the web with much the same tools? And I'm delighted to let you know that there's been quite a lot of different tasks that people have employed this in. So what I'm going to do now is basically run through a bunch of examples of people who do more interesting research than I do, who have used mouse view in similar contexts. So reading. Obviously, the first example I gave was reading. So we're going back to basics. And the top, it doesn't really come through very nicely on the screen here. But you might see there's a few slightly darker bits. There's blurred words. So these researchers took the blurring to quite a large extent. It's a setting. You can set it a bit lower. I think might be okay in this regard. But these are a bunch of papers where they essentially did this kind of blurring approach over reading behavior. And it makes for a way to do reading sequentially online. Often what people use eye tracking and reading for is to see which words do I hang on and which do I skip over, how long do I hang on to certain words, when do I go back to previous words. And this is a really neat way of implementing that in a setting where you can't actually measure eye movements, but now you can actually control what people are seeing, right? So it's a nice approximation of proper reading. The top example, Hassel and Kay, they use this to show that words that are similar in sound, but not similar in semantic context, actually help you find the semantic context of the word that is similar in sound, which is slightly, like, I find that weird. Maybe you activate words not just in a kind of semantic space, but also in a verbal space. This bottom paper, Wilcox et al., is a little bit cheeky. They present basically the same tool that we present. They cite us being like, oh, this is a similar tool, but our tool is optimized for reading. And then they present what looks like the same tool, which, you know, is entirely fair because we were also a bit cheeky because I said, like, we are not the ones to invent this. Like, this has been something that people have been using since 75. So, you know, ever so slightly cheeky, but entirely acceptable. What they did do, though, is this really nice investigation of how this actually speaks to reading behavior. So what you're getting from these mouse movements is on the left, essentially movement across all of the words. The gray kind of vertical bars are different words that they put in there. So you can kind of see as people are reading through the scene, what does their mouse coordinate do? And you can actually identify moments of relative stability that look like fixations. You can identify different types of movement between them, and you can do this at individual level, right? So these are 4 different participants on the same sentences, and you can see slightly different strategies of reading. You can also see people looping back and people going in between different lines. So it's really approximating the exact thing that you would use eye tracking for in reading research. And in fact, some of you might have tried other reading approaches. So these are slightly different in the vertical columns, slightly different types of things you can measure. The top here is the kind of mouse-related implementation, and the bottom here is another implementation you could do, right? You can click through words in a sentence, like self-paced reading is another often used online approximation of reading research. And the idea there is essentially you have a whole sentence and you can just click next word, previous word. It mimics reading, but is not quite as natural. And especially those jumps back into a sentence. You can imagine a sentence where there's a bit of an ambiguity in meaning, and only later in the sentence is that resolved. And now suddenly you have to jump back all the way to the start to reinterpret a word that you can't really approximate with the button pressing, right? And you indeed see that even without those kind of garden path things, these are slightly nicer correlations between the mouse method or the button method and eye tracking on the y-axis. So this is like the mouse approximation. It's just a better approximation of gaze tracking in reading than any other method that we know of is. This is again back to preferential looking, but now more clinically relevant preferential looking. And this answers the age-old question of what happens if I show snakes to people. So this is a sample of healthy controls, and they show kind of approach behavior towards these snake images compared to the neutral ones. Maybe a bit more exciting to see a bunch of snakes. So people look at them a bit more, and they kind of go back to 50-50, can't really be botheredness. But then if you take a sample of people who have a specific phobia for snakes, we see this avoidance behavior. And this is a really nice kind of, it also exaggerates over repetitions. So I guess once it becomes clear that what we're dealing with is a snake, we're trying to avoid it a bit more. And this is a nice clinical measure. So this is the top one, Ronco et al., and then 2 other studies by the same group. What they've essentially tried to do is use this kind of avoidance measure as a metric of how different aspects of either CBT or things relevant to potentially using in CBT context actually work to reduce that gaze avoidance. So suddenly we have a tool that we can use on the web to test patients, if you want to call them that. Another application is in sex research, and this looks a bit silly, I guess, to many of us. The bars are added by me. They weren't there in the actual study. The idea is essentially that you can use this technique to look at different bodies. They can be clothed or in kind of sexually explicit whatever to call that pose. There we go. So this again, it's kind of silly. But this is something that's often used in sex research to kind of gauge interest from, for example, men to men, men to women. Obviously, difference between what kind of orientation you have. And this really nicely replicates on the left, a study in a smaller sample, on the right, a replication study. In a larger sample, these interests, right? So this is a purely heterosexual population because it was a kind of initial try. But the essential kind of pattern is that in triangles, you have these non-sexual options as well. And women look at women a bit more compared to men looking at men. Bottom is male targets. So you see that kind of crossover, but people start looking at sexually explicit images a bit more, which is kind of obvious, but you kind of replicate that bias in this case, heterosexual looking behavior. And again, this is something that's maybe a little bit silly for most of us, but it is a useful tool to then use in kind of clinically relevant populations where this might be different. It also did actually appear in one of the major journals of the field, and Sonia Milani, the first author of this, won a prize for this at one of the SSSS conferences. So, you know, within the field, despite it maybe looking a bit silly to us, apparently a really useful tool. Last clinical example is negative attention bias. So people often work with these kind of displays. And the idea here is essentially there's a bunch of different faces with a bunch of different kind of facial expressions. And in some populations, for example, people who suffer from depression, you see that they might look more at faces with like negatively valenced expressions. So they might look more at the sad faces on here, for example. Easy to replicate in the mousey environment. And indeed, the paper there, McNamara and Beaver, shows that this really maps on very well to what you would normally see in the lab. So again, a nice validation in the clinical population. Task that's close to my heart, visual search in a very interesting kind of foraging, almost literal foraging kind of way. What we have is a network of paths. The green bits are goals where you want to end up. The spokes in here are invisible until your spotlight is over them. And the spotlight here is kind of indicated as a blue thing. The spokes are kind of drawn out just to like make it clear where they are. Essentially people try to kind of navigate over this to find a goal. And you see that it works out quite nicely in terms of where people search. So the red bits are people searching over paths. The blue bits are people searching outside of those paths, maybe exploring behavior. The actual paper has this really complicated physical model of how this kind of search happens. It's honestly worth a read. But I'm going to skip over all of that. It's just a demonstration of, hey, look, another task where this is, you know, an approximation of real gaze behavior. Visual working memory, this is a very classic remapping task. At least I would call it a remapping task. The original authors, they call it a visual working memory task. But the idea is you have something on the left and you're trying to replicate it over here. So you have to look across, remember where things are, pull them in from the sample display and just pop them into the array as you memorize them. And it works obviously by, you know, blanking out the bit around the mouse. So it looks a bit like this. Where we have a aperture, we're moving around, we're kind of looking at our memory array. Remapping is made necessary by the fact that we're moving across. The first trial was really short because we're also doing a confidence measurement here. I say we, but it's these authors do that. But yeah, the bottom line is that we can't cheat by looking over and then trying to kind of mouse around. This is really like an actual remapping task where once you make an eye movement away from your target, it's kind of lost in memory. Or at least it's still in memory, but obviously the remapping needs to be done and there's no direct kind of visual analog. So in the papers I just set up there, a lot of these papers go into, at least one of these papers goes into the mechanics of why we did a sampling from the real world, even if we have the same information in visual working memory. And some of the later papers listed there kind of look at the dynamics within visual short-term memory of like how strong are these things, whether prospective items are also kind of weighing on our memory as well. So again, useful tool in a place where normally eye tracking would have been used to do this kind of remapping investigation. Right. So turns out there's a large literature in comparing humans to whatever flavor of neural network you prefer. And this is one of those papers. Ignore this. This is the architecture of some of those neural networks. It's not going to be super important. This is the important bit. What we have is unrestricted viewing for humans versus restricted viewing with larger or smaller apertures. And they try to approximate that with the kind of visual field, if you will, for the CNNs that are training on the same faces. And what you're seeing is that for those networks, they get really good at recognizing, regardless of the kind of restrictions you put on the network. Whereas with humans, like proper real humans, this is unrestricted viewing. So, nice RC curve, really nice. And in blue and green, we see when there's restricted viewing. So people just get a lot less precise, which is not at all replicated by these CNNs. So I guess it's a nice way of probing whether or not some of these fancy models are similar to humans and in what ways, which is close to at least some of our hearts. Jeff, you'll be delighted that they are not at all similar in this case. There's another example of this by Chris Summerfield, and a similar kind of learning experiment. There's also a quite interesting way of probing, hey, how does human learning actually happen? Just to kind of offer some fair and balanced kind of opinions, I've shown you success stories, these things where we have a good replication. This is it's honestly, I couldn't actually find a paper showing the same thing. I'm hoping it's in the works, but not entirely sure. But this is why it's really nice that all of our theses are kind of published online as well. This is a master's thesis, but it's a really impressive one. Carissa Payne, if you want the author name, it's on the bottom there. But what she did was there's various, but there's a really nice kind of open data set, DEIM. It has a bunch of videos and eye tracking movements on those videos. And what Carissa tried is approximating the same behavior using a mouse view kind of analog. And what you see on the left is the mouse behavior, and on the right is the gaze behavior. And this is one of 27 videos. All 27 heat maps are in the thesis. They all look like this. I didn't just cherry pick one out of them. This is really nice overlap between the two things, you would think. But then this is a dynamic stimulus, right? These are videos that we're showing. And it turns out that there's actually quite a big difference between the mouse and the gaze viewing in here. And on the right, you see eye movements. And this is just one example participant, but it illustrates the point that Carissa and now I am trying to make. And it's that these are centered on fixations, and you barely see any of the transitions between them. That's because this is a pretty low resolution eye tracker, low temporal resolution. So most of the saccades aren't really captured. So you basically just get a bunch of fixations out of there, and that's kind of it. And again, eye movements are super fast, right? It's ballistic things. So what we see instead in the mouse movements is this kind of blur across. Again, people are much slower on this, so you'll find that people following along with the video are actually a bit too slow to follow all the action. So this is quite a fundamental difference between these two things. The other thing is that people are fundamentally in the dark here. The blur is a thing that we do on the basis of a screenshot that we then kind of superimpose over a web page. And it's quite a computationally, it's an expensive thing to do. So it takes a little bit of time. So you can't do this on a video that's just showing at like 30 hertz, right? So instead of doing the blur, this is a complete darkness over the video with just the aperture around where the mouse is. So they're not just figuratively in the dark, kind of moving their mouse around. They're quite literally in the dark, moving their mouse around. So this is a potential kind of problem if you do more dynamic kind of stimuli, right? We can't really approximate that super well with mouse view. Final example, I promise, and the most fun example in the whole thing. So who's familiar with the Mandela effect? Fantastic. All right. So this is a very, very frustrating effect where the name is from Nelson Mandela, who some person, some blogger on the internet, I think, if I remember the story correctly, it doesn't really matter. Just believe that this is the case and don't look it up later. They had this really strong memory of Nelson Mandela dying in jail, which obviously hasn't happened. I see one person nodding along. Maybe you recognize the effect, or you also think that he died in jail. Okay, excellent. All right. I didn't find that particular example very strong. I obviously didn't have any memories of that time. I'm Some of us might. But what I do find a very strong, a very frustrating part of this is that on the top here are a few examples of well-known visual icons that we've all probably have seen at some point. On the bottom are the visual Mandela effect kind of stimuli. These are stimuli that you might think are right, but these are the actual right ones. And I think we all probably have different preferences in this. But what really frustrates me is that C3PO over here, one of the staples of my childhood, had a right leg that was slightly off color. I recognize him as this, like just a completely golden man. Apparently that's wrong. Curious George, also very frustrating, doesn't have a tail in the original there. What? And Pikachu with the little bit on the tail. I have drawings of my own childhood drawing Pikachu like this. It's wrong, apparently. This is him. What? Anyway, they found quite a few of these examples that they just scoured the internet for. And then so this is a frustrating effect. And maybe you found one of these things in here that you recognize in the bottom row, but was actually the top row. Maybe you haven't, at which point I guess it's not as frustrating for you as it was for me. But this is a really striking thing. And what these authors were trying to do is find out why. Why do we do this? And one of the first kind of logical things to do there, I think, is to find out, like, where are people looking on these images that they have these confabulations in them? So you can do that with eye tracking, but obviously the whole point of this is to show you that you can also do this with mouse movement tracking. So you get a nice flick flash and then a mouse tracking kind of spotlight search, essentially. And then afterwards, you get the kind of regular versus Mandela condition. They also have a condition where they make a salient change, but along the same lines as the Mandela kind of replacement, but it's not something that people commonly experience. So the Mandela thing is that something that people very commonly report. The other change is a nice control condition. Just to kind of reference that, they did some better experimentation I'm outlining here. The mesh ones on the right here. Anyways, correct responses, incorrect responses, i.e. actual things, Mandela things. And the heat maps look somewhat dissimilar, and they kind of maybe, if you take the difference, there's a few bits here that look a bit hotter or not. None of this explains why we do this. Like there's no overlap between any of these gaze movements and like the later Mandela experience. So an astounding null effect that makes this kind of experience even more frustrating, because apparently it doesn't matter how you look at these things. There's a kind of holistic experience of Mandela-ing. This is one of the experiments in this paper. And to give you kind of a bit of a treat after this super boring methodological talk, this is nothing to do with mouse view anymore, but this is another experiment in that same paper that also mouse viewed the items. Where on the left we have the originals, and then they made people draw out the originals. And in the drawings, which I find delightful, like this is proper in the wild research, as Ian would put it. We can see in these drawings where people have Mandela, like the Volkswagen logo that has the separation that isn't quite there, it isn't quite there. The tail in Curious George. I find it particularly hilarious that they recognize it here as the one offshoot of a line. But it's very clearly there as well. The legs in C3PO, which I would most definitely have gotten wrong. So, nice demonstration of this kind of in the wild thing, where this, again, has nothing to do anymore with mouse view, but does show the same kind of findings as the mouse view experiment in this did. So, to conclude, we show this kind of open source toolbox that you can just use. You can plug it out as one of the tools that is readily available on Gorilla or PsychoPy or JSPsych. It's a valid analog of eye tracking. I've shown you quite a few examples. We've done very heavy quantification on some of those examples, less heavy quantification on others, but still kind of the overall looks are similar enough, I think, that we can make a decent case for this kind of mouse viewing approach being qualitatively similar, and in many cases that we tested, quantitatively similar to actual gaze tracking, particularly when it comes to overt eye movements, is as reliable as eye tracking is, in the places where we've tested that anyways. So whenever somebody next cites this one paper at you, that they do this to me a lot. I'm not sure whether you have the same experience, but as a cognitive scientist that works in fields where there's also quite a few people who have very heavy questionnaire methods, I always get this one paper cited at me that shows that the reliability of our experiments is really poor. I constantly cite this paper at them, being like, oh, yeah, that might be true in general, but look at this, high reliability. And finally, Mouseview can therefore replace some of the eye tracking that we do, with a strong note that it does look like we're kind of skipping over the kind of automatic attention, or I guess the fast early component. Maybe it's there, maybe it's not there. Maybe this just reflects the kind of overt attentional allocation over space. Right. Thanks very much for your attention. If there's any questions, we have to take them.
Thanks very much, Edwin. I expected like a wild card. A lot of interesting stuff.
If you think I'm a wild card, sorry, if you will indulge me for a few more moments to show you something that Tom cooked up. So Tom, being Tom Armstrong, who I'm sure we've had similar experiences, right? During the pandemic, we were in our homes, we were kind of stuck inside. I started simulating like 100,000 years of human evolution. Tom had a slightly different. Tom had a slightly different idea. Sorry, if I can actually get it on my screen. Hey, there we are. Just making sure the sound is also coming through in the same right place. There we go, HDMI. So Tom did this. You know, it's a very strategic way to avoid any questions as well. You're slowly taking out the time.
Look at them,
That's Tom.
all bright-eyed and bushy-tailed. Seems like they've forgotten a thing or two about eye tracking.
The sanitize. So many surfaces to clean. The chin resting. The pressing of the buttons and the waiting. The detecting of the pupils. The calibrating. And the inevitable recalibrating.
I guess it's all worth it when you get that sweet eye tracking signal. If only there was another way to get a direct and continuous measure of overt attention.
Don't worry, I'm a programmer.
Silence.
I've been tapping away. I've come up with something new. I found the answer to our problems. Mouseview.
And now for our next guest, creator of the Pi Gaze toolbox that revolutionized eye tracking, and author of several best-selling books, including Python for Experimental Psychologists, 50 Shades of Python, and Eat, Pray, Love Python.
Edwin Dalmaijer, and I've spent my entire life building cheap software for things like these, eye trackers. Turns out, I've wasted my entire life. You see, we developed Mouseview.js, which is an online eye tracking alternative that allows you to do attention tracking in the browser. It's entirely effective given the right circumstances, and you can use it in all of the big platforms like Gorilla, JS Psych, and basically everything that plugs into JS.
This was me forgetting the name for PsychoPy. anyways, there's a whole extra infomercial aspect after that as well. But yeah, that is proper wildcard behavior. That is Tom doing his video advertisement skills.
That's great. So any quick questions for Edwin from the crowd? Yes, Nick?
When you're comparing your mouse stuff with your eye stuff, the eye stuff is essentially quicker, right? You've got more
Yeah.
stuff to learn. If you normalize one to the other, does that get rid of that weird thing that happens in the first second? Because that's obviously where that's going to be maximized. So if you normalize the time course, your x-axis is the same for both, which seems an unfair comparison.
Yeah, I have a short answer to that, which is not fully, and I have a longer answer to that, which I hope I have an example of here.
It depends.
Yeah, the answer is it depends. The cop-out answer that everyone loves all the time, all around. I don't think I have it here. And so what I was trying to look for, we did a scan path comparison as well, which kind of is what you're asking about, right? Because it in some ways normalizes the kind of movement from one bit to the next across the screen. Exactly. Yes. Yeah. So what we did is we mapped that onto a kind of singular space out of a like XY time space into a two-dimensional space, projecting it using UMAP. And also using multidimensional scaling, where you find some similar things. And if you project that, you get this nice kind of differentiation between the different trials, where eye movements, or at least the kind of progression between AOIs is a bit different. That's similar qualitatively between the gaze and the mouse tracking. So in that sense, it looks that scan paths are roughly similar. Now, I say that on the basis of this relatively complicated kind of analysis where we project everything into a two-dimensional space and then compare those spaces to each other. There are other people who, again, master's thesis, I don't really know what the veracity of the actual data is because they haven't necessarily published alongside. They did similar kind of scan path analyses and found actually the relationship isn't as strong in completely different stimuli. This is more like browsing through essentially web pages. And also we do find that the kind of first initial component is rather blunted in the mouse view things as well, which is why I kind of stress that it's probably the reflexive aspect of first eye movements. So it's hard to suppress eye movements, right? And it's much easier to suppress this kind of overt mouse movement to a thing. So I think we have a difference in the kind of expression of eye movements to things that are hard to suppress. And on top of that, you're absolutely right. If you do compress it into the same time space, overall, the rest of the gaze pattern looks very similar, at least in our hands, but not for all stimuli.
A quick question. So in the cases where, so people also use sort of mouse tracking as a way to explore decision making.
Yeah.
So in those cases, like where the task, people have to explore and also make a decision.
Yeah.
I think that would actually interfere with what you see in terms
Maybe.
of
So those are those clever tasks. We had like one option on both sides. You have the kind of mouse progressing upwards, and you have to then go one or the other way. Good question. I think it'd be hard because what we're trying to do is map it to perception, and therefore you wouldn't actually see those extremities, right? So the one place where I see this working is teleforaging, where you basically do some of those Sahakian-based pairs did something similar, right? Where you're trying to teleforage for information in the environment. And there you get the same kind of pattern as you would see with eye movements, where people sample the environment to get information that they could have easily had in working memory as well, probably as an expression of their uncertainty of the outside world. So if you want to talk in decision-making terms, I think that's the best place to start looking, or to follow up some people who've done some perceptual work.
So, yes, Ian?
Following up on Nick's question to a certain extent, but in a slightly different way. Obviously, when we make saccadic eye movements, we have saccadic suppression.
Yeah.
So vision is absent between the movements. So we just looking up at the patches.
Yeah.
It looked from your demonstrations that with the mouse movements, you're quite often catching the bit in between.
Yeah.
How important is that? The difference, I think?
Good question. So if you move the mouse rather quickly, which is what sometimes happens in these kind of by image displays, you don't really get anything in the middle because the mouse moves within a few frames of what we can update, it moves across. So you do have some saccade-like behavior, but it also seems that people are a bit less saccadic and a bit more kind of smooth over some of the areas when they're doing some of these tasks. I think the display that I put on was an example of the researchers themselves. I don't know whether that was real participant data. I'd have to look that up. So it might be that they kind of exaggerated the smoothness. I see participants who do act a bit more kind of saccade-like. And I also see participants who just use this as a searchlight to slowly go across stimuli. So the answer is sometimes you get it, sometimes you don't. The second part of the question, how important is that? Probably depends on what your question is about the actual stimuli, right?
So a practical question, could we or someone hack your code so that it at beyond a certain velocity it just goes blank? Or just
Definitely. Yeah.
And then as you accelerate, you can bring the image back on again, because then you can simulate almost exactly what's happening with saccade suppression. Yeah.
Absolutely. Yeah. So if you wanted to look at saccades, I guess that is a way of doing it. Although I would again hesitate that none of the other saccadic dynamics like curvature are captured here, right? So I think when I say eye tracking here, I primarily mean kind of gaze tracking, where we go from different areas of interest or kind of sample a visual display. And I mean less the other types of eye tracking that we do, where we look at pupil size, for example, or indeed secundometrics.
So quickly, Ubuntu and Biography.
Yeah, we can still anywhere where something like iconic memory or short-term memory or memory components are really needed. Should that not negatively interfere to see certain decays of memory? But people are not the same way that
yeah. So if I can summarize, sorry, if I summarize it correctly, you have more time that it takes to explore the screen, and therefore the kind of degradation in memory is just kind of happening as you're moving along, and therefore you're losing more time and therefore losing more memory trace as well. Yeah, that's very possible. Yeah. I will note that, so the one piece of evidence we have here is the Sahakian papers. And if you compare that to this piece by Sanjay Manohar on teleforaging, you actually see somewhat similar behavior, at least qualitatively, in the sense that even when people are moving their eyes around this visual display that has information on, they really often resample the same information. So I'm not sure whether that's fully just the reduction of the memory trace or a strategy where we know that the outside world is super high resolution, and our inside representations are subject to degradation, as you actually point out. So I guess you see similar behavior between those two different options, but also depending on the design, it's very likely that this mouse viewing thing might be a downside if you are hoping to get good memory traces and get saccadic, or not saccadic, but eye movement behavior on the basis of those. So I guess depending on what your design is, you might want to be very careful. And I guess in the remapping, because we have a higher threshold, I suppose, than our degradation threshold is, we see like movements back anyway, whether eye or a mouse. But in another kind of scenario where we would dip below that degradation threshold, that might be a real problem. Yeah.
Okay, just go with the now it's probably about.
I have two questions, but I will start with the first one, just to get if I understood it right, because it looks very interesting, but it's the first time I see something like this. So the way you perform the experiment with the mouse is you create this variation.
So you create it?
You create this
Yes, a variation. Yes, yeah.
So when you start it, is there any spatial bias?
So it depends. What I do in my experiments is I have a fixation trial where they have to click on the middle of a screen, like on the fixation cross, and therefore all the trials start on there. You could, like, it was kind of implicit in some of the heat maps where you saw quite strong heat map in the middle for the mouse and less so for the gaze. That's because of that fixation starting there. So that's analogous to, I guess, tracking experiments where you do a drift check in between, and therefore you center people's, I guess, gaze in the middle. But this is a design choice, right? It's kind of up to you. It basically follows where the cursor is at any given moment. So if a participant had it in the corner and you didn't correct for that, it's going to show up in the corner or wherever else on screen.
And the blurring was quite intense, right?
Yeah.
Because, well, I'm not an expert in this field, but it looked like a bit more intense than I would expect, like the White House, right?
So
That's like kind of the exploration.
yeah, likely. So just to this is a hard problem to get
Yeah,
right,
yeah,
because
of course.
when we deploy this on, say, Prolific through, say, Gorilla, everyone's screen is of a different size and everyone's set at a different like distance. So what we did is kind of roughly eyeball like where are people likely going to be, how big are most screens. Alex also worked for Gorilla for a while and did this wonderful kind of test timing study where there's a lot of participants and the data on their setups in there. So we had some insight into what you normally find in the wild. So we basically eyeballed that, kind of squinted and figured, you know what, at these conditions, this kind of blurring roughly maps onto human peripheral vision. And this kind of aperture roughly maps onto the size of the fovea and, you know, towards parafovea. And we use that, which is just in a setting that for some people will be absolutely on it, for other people nowhere near. So that's a bit of a tricky thing. It is also settings you can specify yourself. So if you wanted to go for a larger aperture, that's entirely possible. I realize that some people are not going to use this as like visual mimic, but rather as spotlight, for example. So it is all customizable. The way that it works is it captures the HTML, it employs a blur, and then projects that on top of the page, and then, you know, cuts out the aperture in there. Sorry?
I thought it was an overlay.
Yeah, exactly. Yeah. So, you know, the SD of the Gaussian blur, you can just set yourself to a higher or lower thing depending on your criteria are.
Yeah, I mean, those questions stem out of the fact that we noticed mostly for visual quality assessment, that's where my background comes. We noticed that the difference in the distance between the viewing distance plays an important role in people rating, and that of course has to do with the aperture of their eyes and such. But I was also thinking how that could be implemented at the video level, like for dynamic changes, because I think that's anyway. I think it's a big discussion.
So let's have that discussion.
Yeah.
Sure. Cool, thanks. Thanks again, Edwin, very much.
Thank you.